Welcome everyone, Tashians to sleep by. Tonight, we're drifting into the gentle mystery of an object that has puzzled astronomers around the world. 3I Atlas. It was expected to be the third known interstellar comet, following in the footsteps of Oumuamua and Borisov. Yet something about it feels different. Its faint glow, its unusual trajectory, its uncertain nature, all of it invites us to ask a question that lingers softly in the night sky. What if 3I Atlas isn't a comet at all? So settle in. Let your breathing slow. Let your thoughts soften. And let the universe whisper its secrets as we explore what this strange traveler might truly be. When 3I Atlas first appeared in the sky, it arrived with far less fanfare than you might imagine for something traveling from beyond our solar system. The discovery was made by the Atlas Survey, a network of sky-scanning telescopes designed to watch for near-Earth objects that might pose a hazard. The system is tuned to pick up faint, fast-moving objects, and when the signals of 3I Atlas were first processed, it seemed to fit the early profile of another interstellar comet, following in the path of the first two visitors from beyond our sun's gravitational embrace. Yet something subtle, quiet, and peculiar stood out from the very beginning, as if this visitor carried with it a hesitation about what it truly was. Its brightness was modest, oddly stable, and its predicted activity did not unfold the way cometary models expected. When scientists expect a comet, they expect behavior, the warming of sunlight that releases gas, the visible growing of a coma, the feathered glow of a tail stretching outward. But 3I Atlas was not behaving, not changing, not expanding in the ways that made sense for an icy wanderer warmed by a star. Instead, it seemed to hold its light with a strange stillness, as though it were less a drifting snowball from another system, and more a quiet stone carried in on a cosmic tide. The first puzzle arrived in the form of photometry, the measuring of brightness over time. As Atlas and other telescopes around the world captured data each night, astronomers anticipated the gentle rise in brightness that comets typically show as they approach the sun. This didn't happen. Instead, the light curve of 3I Atlas stayed surprisingly flat, almost subdued, missing the characteristic surge caused by sublimating ices. Astronomers reviewed their instruments, checked calibration files, compared data between observatories, but the signs remained the same. The object was not brightening the way a comet should. Its behavior was reminiscent of Oumuamua, the first interstellar visitor, which also showed none of the clear visual markers of a comet, behaving more like an inert object. Scientists found themselves returning to the same question late at night, running simulations under soft computer light, trying to understand how an object could appear comet-like in orbit, yet refuse to act like one in nature. Its trajectory, however, held the unmistakable signature of an interstellar origin. When something enters our solar system from deep space, it usually follows a hyperbolic path, a shape that is not closed like an ellipse or a circle, but open. The energy required to follow such a path almost always means the object is not gravitationally bound to the sun. 3I Atlas had a high eccentricity, meaning its orbit was stretched so far that it would never return. It was simply passing through, a cosmic visitor on a one-way journey. This alone told astronomers that the object was unlikely to have formed here, but determining what it actually was demanded careful interpretation, a calm sifting through possibilities, and the patience to understand that an interstellar object does not owe us familiarity. Spectroscopic data added the next layer of uncertainty. When a comet begins to warm, even slightly, sunlight breaks molecules apart and creates signatures in the spectrum, markers of carbon, nitrogen, water, dust, and gases that carry the fingerprints of distant planetary nurseries. But the spectrum of 3I Atlas was faint and nearly featureless. Instead of clear cometary emissions, astronomers observed something quieting, more muted, as though the object contained little accessible ice, or perhaps had undergone billions of years of cosmic weathering that transformed its surface into a hardened shell. Interstellar space is a place of extremes, radiation, micrometeorite impacts, and eons of silence where a body can lose its surface volatiles and become a dark, dormant relic. If 3I Atlas had been traveling for millions or billions of years, it was conceivable that most of its original ices had already evaporated long before entering our solar system. Yet if it were truly a comet, deep layers of ice should have remained intact and should have awakened, even slightly. As it neared the sun, the absence of activity pushed scientists to reconsider their assumptions. Another confusion arose from the object's apparent size and rotation. Early estimates suggested that 3I Atlas might be relatively small, and its rotational characteristics did not match the typical tumbling motions astronomers associate with elongated cometary bodies. Instead, it seemed more stable, more compact, and perhaps composed of denser materials. Some models proposed that it could be rocky or metallic, not icy, aligning more with the nature of an asteroid. But interstellar asteroids are rare in our detections, largely because they can be dim and difficult to spot. If 3I Atlas was one, then its arrival marked only the third such interstellar object ever observed, each one carrying with it a lesson about how much more exists between the stars than we once imagined. Observatories across the United States, from Hawaii to Arizona to New Mexico, joined the effort to characterize this unusual traveler. Even amateur astronomers contributed data, capturing faint specks of motion across long exposure frames. As more observations accumulated, the orbit became clearer, confirming that the object had entered our solar system at high speed, influenced only gently by the sun's gravity, then continued outward, without slowing enough to be bound. Its path was consistent, but its identity was elusive, demanding both scientific precision and imaginative openness. It is often in these moments of uncertainty that astronomy becomes a uniquely poetic science, bridging the line between what we know and what we sense. The historical context further deepened interest in 3I Atlas. The first interstellar object ever discovered, Oumuamua, had already challenged expectations with its cigar-like shape and puzzling non-gravitational acceleration. Borisov II was more conventional, a clear comet with visible outgassing. With only 2 prior interstellar objects in our catalog, there was no established pattern, no well-defined set of rules these travelers were supposed to follow. So the discovery of a third object that didn't neatly resemble either of its predecessors raised a quiet tension within the scientific community. Was 3I Atlas the beginning of a new category? A hybrid class of objects shaped by conditions we seldom encounter? Or simply a fragment so ancient and altered by interstellar radiation that all its cometary character had faded into a dormant state? Astronomers examined how objects are ejected from young star systems, how gravitational interactions with giant planets can fling debris into deep space, and how the journey between stars might strip away the layers that once defined them. In this slow, methodical process of discovery, astronomers recognized that 3I Atlas was offering an opportunity not just to classify, but to expand the language of interstellar science. It reminded researchers that their expectations were based on observations confined to one star system, and that the galaxy holds countless worlds shaped by conditions far different from our own. Each visitor from beyond carries with it the quiet possibility of rewriting something fundamental. And 3I Atlas, with its resistance to simple labels, invited scientists to listen more closely, observe more gently, and imagine more broadly than ever before. From the moment astronomers noticed that 3I Atlas was refusing to behave like a comet, the next most compelling possibility began to take shape. Perhaps this visitor was not an icy wanderer at all, but an interstellar asteroid, a dense and ancient fragment from a distant planetary system. This idea drew strength from the object's muted brightness, its lack of a visible coma, and its unusual steadiness. Interstellar asteroids, unlike comets, carry no shimmering aura of vapor. They glide through space like dark, hardened stones, leaving no trail of evaporating gases. The possibility that 3I Atlas belonged to this category opened a new path of inquiry, one that carried astronomers far beyond the familiar patterns of comets that swing through our solar system, and into a deeper understanding of rocky bodies shaped by the harsh weather of interstellar space. To understand why this explanation gained traction, One must consider what distinguishes a comet from an asteroid. Comets are known for their volatile ices: frozen carbon dioxide, frozen water, methane, ammonia, and other delicate molecules that evaporate when warmed by the sun. This evaporation creates the glowing atmosphere known as the coma, along with the majestic tail that stretches for millions of miles. Asteroids, by contrast, are typically rocky or metallic, formed in the inner regions of young planetary systems where temperatures were too high for volatile ices to survive. If 3I Atlas had originated from such a region in some distant star's early formation zone, it would have been devoid of ices from the beginning, and thus incapable of producing any of the cometary activity astronomers initially expected. As telescopes began collecting light from 3I Atlas, astronomers looked for hints of sublimation, expecting at least a faint glow as it approached the sun, but as data continued to accumulate, the glow never appeared. This absence of cometary behavior suggested a solid, rocky composition, and while this alone did not prove the asteroid hypothesis, it deepened the intrigue. Interstellar asteroids are rare in our detections, not because they are uncommon in the galaxy, but because they are difficult to see. Their surfaces are darkened by cosmic radiation, and without reflective ice or outgassing, they can pass through the solar system almost unnoticed. The very fact that 3I Atlas was discovered at all suggested that it might be larger or more reflective than most such travelers, or simply that the Atlas survey had caught it at just the right angle as it drifted past the sun. Further clues came from the object's rotation. When astronomers study the brightness of a celestial body over time, they can detect subtle fluctuations that reveal how it rotates. Elongated or irregularly shaped objects tend to tumble in complex patterns, causing the brightness to rise and fall in predictable cycles. If 3I Atlas had been a comet shedding material unevenly, its spin might have been affected by jets of gas erupting from beneath its surface. But the light curve of 3I Atlas appeared unusually steady, showing none of the irregularities associated with cometary jets. This steadiness, though not conclusive, again pointed toward the idea of a solid, rocky structure, one that had likely survived millions or billions of years in the emptiness between stars. Asteroids that travel through interstellar space experience an environment unlike anything found within the protective bubble of our solar system. They are bombarded by high-energy cosmic rays, struck by micrometeorites, and exposed to deep cold for incomprehensible lengths of time. Over such timescales, their surfaces become coated with a thick layer of radiation-processed material, darkening them and often reducing reflectivity. This leads to an object that can appear ghost-like, dim, slow to brighten, and difficult to decode. If 3I Atlas had been drifting for eons, its outer layers could have transformed into a hardened shell of carbon-rich compounds, shielding whatever internal structure it once possessed. This would explain its muted appearance and lack of visible emissions. The asteroid hypothesis, in this sense, carried an elegant simplicity. It fit the behavior, the brightness, and the silence of the object's spectral readings. Still, astronomers recognize that interstellar asteroids can be far more complex than their solar system cousins. When a young planetary system forms, its first few million years are chaotic. Planetesimals collide, merge, shatter, and scatter in every direction. The gravitational pull of giant planets can fling rocky fragments into interstellar space, where they embark on lonely journeys that last longer than entire civilizations. If 3I Atlas was one such fragment, it could represent a piece of a planet that never formed, a shard from a larger body that broke apart, or even a small remnant produced by violent interactions with a giant planet in a faraway system. Each of these possibilities carried a quiet sense of wonder, the idea that this small, faint object drifting past our sun was once part of a world that orbited a different star. Spectroscopic observations sought to answer this question. Scientists hoped to identify reflective materials, iron, silicates, carbon compounds that would help classify the object. But the data was faint, carrying only hints rather than clear signatures. Even so, the lack of icy emissions strengthened the idea that the object's surface was dominated by hard, non-volatile materials. Some researchers propose that 3I Atlas might be similar to certain types of carbonaceous asteroids found in our own solar system, which are rich in organic compounds and darkened by billions of years of radiation. If that were true, the object could provide insights into the chemistry of other star systems, offering a rare opportunity to compare materials formed around distant suns. Simulations of the object's trajectory further reinforce the asteroid interpretation. If 3I Atlas had been a comet, its non-gravitational forces caused by outgassing would have altered its path slightly, pushing it off its gravitational track. But early analyses suggested that its motion was remarkably smooth, guided almost perfectly by gravity alone. This behavior matched what astronomers expect from a solid, inactive body rather than a vapor-spewing comet. Every new calculation nudged the interpretation a little closer toward the possibility of an interstellar asteroid, one that retained its stillness even under the warming influence of our star. The idea that 3I Atlas might be an interstellar asteroid carried profound implications. Interstellar asteroids, by their nature, are fragments that reveal how other solar systems formed and evolved. If this object truly belonged to that category, it could help astronomers understand the distribution of rocky material around distant stars, the frequency of planetesimal ejection, and the processes that shape planetary systems across the galaxy. Every interstellar asteroid detected broadens humanity's map of cosmic geology, offering clues about the diversity of environments where planets might form. The asteroid hypothesis also resonated with the story of Oumuamua, the first known interstellar visitor. Like 3I Atlas, Oumuamua showed no visible outgassing, and its unusual shape startled astronomers. While 3I Atlas did not display the same dramatic elongation, its quiet behavior placed it in a similar category of objects that challenge our assumptions. The two bodies together suggested that interstellar asteroids might be more common than once believed, perhaps far more common than interstellar comets. This shift in perspective invited astronomers to re-examine their expectations about the objects drifting between stars, and to consider that rocky fragments may dominate the dark spaces between solar systems more than icy ones do. As researchers continued to gather data, the asteroid interpretation remained one of the most compelling explanations for the enigmatic behavior of 3I Atlas. It provided a coherent narrative for the object's lack of activity, its spectral quietness, its steady rotation, and its gravity-driven motion. It offered a vision of the object as a time-worn relic, shaped by the forces of a distant star system and carried on a journey that spanned unimaginable distances. And if 3I Atlas was truly such an interstellar asteroid, then its arrival in our solar system represented a fleeting encounter with a piece of a world whose story began long before ours ever did. When scientists considered the possibility that 3I Atlas was not a comet, and perhaps not even a typical interstellar asteroid, a deeper and more awe-filled idea emerged, one rooted in the violent, creative, and unpredictable nature of planetary formation across the galaxy. What if 3I Atlas was an ancient fragment from another solar system, a leftover piece from a world that never fully formed, or a shard torn away from a young planet during a chaotic moment in its star's early history? This possibility tugged at something beyond simple classification. It suggested that 3I Atlas was more than just an object. It was a remnant of cosmic history, a traveler carrying the memory of a world that once existed around a star too far for us to see with the naked eye. The idea transformed the object from a distant point of light into a messenger from a place older, stranger, and more mysterious than anything in our own celestial neighborhood. To understand how such a fragment could come into existence, it helps to picture the early stages of a forming solar system. When a new star ignites from a collapsing cloud of gas and dust, it forms with an enormous spinning disk around it rich with raw materials that will eventually build planets, moons, asteroids, and comets. This disk is chaotic, full of collisions, mergers, evaporation, gravitational tugs, and constant reshaping. In the first 10 million years of such a system, trillions of pieces of rock and ice collide with each other, sometimes merging into larger bodies and sometimes shattering into fragments. The early solar systems across the galaxy are loud, with impacts, explosive heat, and violent rearrangements. In these collisions, some material gets scattered to the outskirts of the star system, and some gets thrown so hard by gravitational interactions with giant planets that it escapes entirely, beginning a journey into the deep interstellar dark. If 3I Atlas was ejected from such a system, its age may not be measured in millions of years, but in billions. It could have formed when its original star was still young, perhaps 5 or 6 billion years ago, meaning the object began its journey long before Earth had oxygen in its atmosphere or complex life on its surface. The fragment may have drifted between stars while civilizations rose and fell on Earth, while continents formed, while galaxies collided, and while thousands of other planetary systems lived through their own cycles of birth and destruction. This cosmic timescale adds a layer of quiet wonder to the idea of 3I Atlas as an ancient relic, carrying physical properties shaped by conditions far older than humanity's entire existence. Astronomers studying 3I Atlas considered what kinds of events could have produced it. One possibility is that it came from a young, crowded system where giant planets migrated inward and outward in dramatic shifts. When a giant planet moves through a system, its gravity can act like a slingshot, sending smaller objects flying into new orbits or ejecting them entirely. Such ejections are not rare. In fact, simulations suggest that most young star systems lose enormous amounts of material this way, with untold billions of fragments cast into interstellar space. If 3I Atlas had once orbited such a system, it might have been part of an asteroid belt, or a building block of a planet that never fully formed, or even a piece of crust stripped away from a larger world during a massive impact. In any of these scenarios, the object's composition would contain the chemical fingerprints of a star system unlike our own, a mixture of elements and minerals crafted by conditions unique to that system's formation. Another possibility is even more dramatic. 3I Atlas might have been shaped by a stellar death. Some stars end their life cycles with explosions powerful enough to tear apart planetary bodies, scattering debris across great distances. If 3I Atlas came from a system that experienced such a fate, its material could have been altered by the heat of a supernova or the gravitational disruption of a dying star expanding into a red giant. In such cases, the fragment may carry traces of isotopes or mineral structures that no longer form naturally in the calm environment of mature star systems like ours. These clues would be faint, subtle, and difficult to detect, but they would transform 3I Atlas into a physical record of a star system's final moments, a witness to an event that reshaped its entire cosmic neighborhood. The immense age of such an object would also mean it has endured eons of interstellar exposure. Between stars, space is not empty. It is filled with high-energy particles, stray atoms, drifting dust, and cosmic radiation that gradually alters the surfaces of objects. Over millions of years, these forces harden the outer layers, darkening them, smoothing them, and erasing the softer textures that once existed. A fragment that began as porous rock or mixed ice and dust might now be covered by a protective shell created by radiation bombardment, capable of withstanding the long journey between systems. This weathered surface would make the object appear muted in brightness, quiet in its spectral readings, and resistant to the heating effects of the sun, all characteristics that match what astronomers observed in 3I Atlas. If 3I Atlas was indeed a fragment from another solar system, its chemical story would be written deep inside it, beneath the radiation-hardened exterior. While we cannot retrieve such a sample directly, astronomers often consider how the internal composition might differ from objects in our own system. It might contain minerals formed at temperatures or pressures not found around the sun. It might possess rare isotopes created by the unique nuclear fusion processes of its original star. It could even carry organic compounds shaped by an entirely different chemical environment, offering clues about how widespread life's building blocks might be throughout the galaxy. The mere possibility of such differences inspires the quest to study interstellar visitors more closely. Even if each one remains just slightly out of reach, Another layer of fascination comes from imagining the environment where 3I Atlas originated. Was it part of a crowded system with multiple planets circling tightly around a bright, energetic star? Or did it form in a quiet region, orbiting a faint red dwarf with a slow and steady glow? Was its birth environment similar to our own solar system? Or was it shaped by forces completely foreign to us? Every planetary system has its own personality, its own gravitational rhythms and thermal landscapes, and these variations produce materials with their own unique structures. If 3 Atlas came from a region rich in iron, carbon, or silicates, or from a system with an abundance of volatile compounds, these details would have been preserved inside the object since the moment of its creation. What makes this theory so compelling is not just the science, but the perspective it offers. When we observe an object like 3I Atlas, we are not simply watching a rock move through space. We are witnessing a physical piece of another star's story passing by our own. It is a moment of cosmic intersection, where the history of distant suns briefly grazes the edge of our sky. For a brief time, our solar system becomes the host to something ancient, foreign, and utterly unique. A visitor whose journey will continue long after it has slipped back into the dark beyond the sun. To think of 3I Atlas in this way is to understand it as part of a much larger tapestry, the interconnected life cycles of stars and planets across the galaxy. If this object truly originated from another system's violent birth or catastrophic ending, then it represents a chapter of cosmic history written long before our own world took shape. It tells us that the galaxy is a place of constant change, where fragments of creation drift endlessly between the stars, carrying the silent stories of worlds we will never see. As we reach the end of this quiet journey through the mysteries of 3I Atlas, we find ourselves standing at the crossroads of science, imagination, and the vast unknown that stretches far beyond our familiar solar system. What began as a simple question about whether this visitor is a comet has unfolded into a much deeper exploration of how little we truly know about the material traveling between the stars. By stepping through each keynote, we followed the object from its uncertain identity to its unusual behavior, its puzzling physics, its potential origins, and the profound implications it holds for astronomy and planetary science. The more we examined it, the more 3I Atlas revealed itself as a reminder that interstellar space is not a quiet void, but a dynamic realm filled with remnants of ancient systems, fragments of cosmic histories, and travelers shaped by processes we are just beginning to understand. If 3I Atlas is not a comet, then it represents a category of interstellar bodies that defy our expectations, quietly rewriting the boundaries of what we believe small objects can be. Its irregular activity, its possible non-cometary composition, and its faint, unpredictable responses to sunlight show that the universe is capable of producing materials far more diverse than anything cataloged within our solar neighborhood. It pushes scientists to revisit long-standing models of planetary formation and to consider environments where fragments like this could be forged, hardened, ejected, and left drifting through cold space for millions of years before wandering near our sun. Its presence also reshapes how we interpret faint signals from distant visitors. Instead of relying on the predictable patterns of comets we grew up studying, astronomers must now examine subtle clues, faint variations, and unexpected accelerations, all of which might hint at exotic materials or origins. It influences how we search for future interstellar travelers and how we calculate their trajectories, reminding us that each visitor carries a unique physics born of its own star system's evolution. 3I Atlas becomes not just a curiosity, but a messenger, carrying the chemical fingerprint of a distant world we will never see, offering insight into the diversity of planetary systems scattered across the galaxy. And yet, beyond the science, there is something soothing about contemplating an object like this in a late-night setting. For a U.S. audience settling into a quiet moment, the story of 3I Atlas becomes a gentle reminder that the universe is not static or predictable, but instead, alive with drifting travelers, each with its own story, its own past, and its own silent journey across the Milky Way dot in the end. 3i Atlas leaves us with more questions than answers, and there is something deeply comforting in that uncertainty. It invites curiosity without demanding resolution, encouraging us to imagine what kinds of worlds might have shaped it, what events might have launched it, and what other strange objects may be making their way toward us even now, quietly crossing the deep, cold distances of space.